All right, I want to welcome everyone. My name is Heidi Lapka. I'm Director of Special Projects for IBS, and I want to welcome you to our October Journal Club. These sessions are complimentary to all IBS members with a primary purpose to provide a platform for individuals to present worthy papers in a public setting and to widen the scope of understanding for those papers. Additionally, we want to provide a networking opportunity for IBS members through the Journal Club. I have just a few general housekeeping comments to make before we get started. First, this session is being recorded and will be available for replay early next week on the IBS website under Education and then Journal Club. Please keep your phones or your lines muted. You did come in on a muted line. You will have the opportunity to ask questions during the Q&A period at the end of both presenters. And at that time, you are free to unmute your line and ask questions. And you also may ask questions via the chat feature, and we'll address as many as we can during the Q&A session. So first, as I mentioned, Journal Club sessions are open to all members free of charge and are hosted throughout the year. Today, however, we opened this session to non-members. So if this is your first time connecting with IBS, welcome. We're glad to have you here. IBS is a global family of statisticians, mathematicians, biological scientists, and others advancing in the field of biometry. You'll see just a few of the benefits on the screen that are included in membership, but I encourage you to scan the QR code to learn more about how IBS membership can benefit you personally and professionally. Secondly, I'd like to talk a little bit about our distinguished lecture series. We're really excited to welcome it back. Our first session of 2024 will take place on the 31st of October or the 1st of November, depending on your time zone. Our featured presenter will be Dr. Francis Hui. He is Associate Professor in Statistics for the Australian National University. The IBS Distinguished Lecture Series is a series featuring early career professionals working in the field. They are nominated by fellow IBS members, and the session will be open to both members and non-members. So I encourage you to head on over to the Distinguished Lecture Series on our website. You can do that by scanning that QR code, and you can register today. And lastly, I wanted to highlight our upcoming International Biometric Conference taking place December 8th through the 13th in Atlanta. We're really excited about our program. Again, feel free to scan that QR code, get yourself registered, and get information on all of the scientific programs, networking opportunities, special events, and mentoring programs that are available at IBC. And with that, I'd now like to hand over the program to Jen Lee. He is Associate Professor from the Department of Biostatistics at the University of Michigan. He also serves as the Journal Club organizer and chair. Jen?
Thank you, Heidi. Welcome, everyone, especially those who join us for the first time. Welcome to this Journal Club. Today, we are very pleased to have Dr. Jiaqi Gu joining us to present today. His recent paper was published in Biometrics titled Summary Statistics Knockoff Inference with Family-Wise Error Rate Control. So apparently the large crowd speak volumes to the importance of this topic. So Jiaqi is currently a postdoc scholar in the Department of Neurology and Neurological Sciences at Stanford University. His research concentrates on preference learning, network data modeling, quantitative analysis of survival and public health data, high-dimensional statistical inference with geometric information and statistical genetics. So we also welcome the discussant, Dr. Zhimei Ren, which will lead the discussion today after the presentation from Jiaqi. So Zhimei is an assistant professor in the Department of Statistics and Data Science at Walton School at the University of Pennsylvania. Her research focuses on distribution-free inference, selected inference, data-driven decision-making, causal inference, and survival analysis. So all participants are encouraged to engage in the discussion, ask questions, but we would appreciate if you can leave the question towards the end at the Q&A session. Or during the talk, you can also post your questions in the chat, if you will. So we'll have about 20 to 30 minutes for the presentation, and then followed by 15 minutes-ish for the discussion, and then we have the Q&A. Okay, so without further delay, let's welcome Jiaqi. So Jiaqi, please take it away.
Yeah. Thanks for the invitation for me to present our recent publication, Summary Statistic Knockoff Inferences with Family-Wise Error Rate Control. So I'd like to mention my collaborators, including Catherine Xinrui Yu, Zhang Wengchen, and my advisor Zihuan He in making this happening. So in this work, we have developed a new knockoff filter that can select important features with a family-wise error rate control with only access to summary statistics. So with a potential application in large scale genetic analysis studies. So for the first, I would like to provide you the outline of today's presentation. And firstly, I will introduce the background of our research problem, and then based on what we identify the obstacle of genetic studies, we developed our new methods with both the computational strategies and the theoretical studies. And then I will briefly go through some experiments to validate the empirical performance of our method, and finally to apply it in real data to identify the important genetic variants with a substantial contribution to Alzheimer's disease. So for our study, our research problem is lying in selecting the important features that have a contribution to the response. So here in our problem, we consider the ID observation from a joint distribution of the features X denoted from X1 to XP and the response Y. And our interest lies in the family of conditional independent hypothesis XJs, where we want to infer whether each feature XJ is independent to the response Y, given other features denoted by X minus J. And we are interested in the whole family of hypothesis XJs, where J from 1 to P. That means that we care about all the features. And our target here is to obtain a set of reject hypotheses that denoted by R, such that we have control the family-wise error rate under the target level alpha, which means that we want to ensure that with a probability less than alpha, not larger than alpha, we have made at least one false discovery, which means that with a probability 1 minus alpha, we can confirm that most of our discoveries are true. So in the literature, there's a lot of existing methods have proposed for conditional independent tests, ranging from the parametric test for a linear model, semi-parametric test, or the non-parametric test, which based on the resampling procedures like permutation or bootstrappings. And because of what we concern is about the multiple family of a conditional independent hypothesis, which means that we are doing the multiple testing. So to control the family-wise error rate, people would propose a lot of correction for the multiplicity issues, including the well-known boundary correction and the mother's variance. However, all these methods requires the non-trivial p-values as an input, but this is not always feasible because in high-dimensional, for example, high-dimensional linear model, it is difficult to obtain the non-trivial p-values, and even these p-values may also be subject to, for example, model misclassification, such that make the p-values not valid. So to address these issues, the knockoff filter has been recently developed to infer the conditional independent hypothesis without any assumption imposed on the conditional distribution on the Y given X. So most of these methods follows the following workflows. Firstly, people will generate the X tutors as knockoff to synthesizing them as a negative control of the original feature, such that the knockoff X tutor is independent to the response Y given all observed features. And people will generate the X tutors to be indistinguishable from the original features, such that for any the joint distribution of x and x tutor will remain the same if we swap the corresponding components in x and x tutors. So one example is when x is follow a Gaussian distribution, people will generate the x and x tutor from a joint Gaussian distribution with the same mean for x and x tutor and the covariance matrix as shown in the highlight, where sigma is the original covariance matrix of x and D is a diagonal matrix. So after generating the knockoff knockoff, people would then compute and compare the association scores G1 to GP and G1 tutor to GP tutor corresponding to x and x tutors. The philosophy under knockoff is that for example, here we take a comparison between the x1 and x1 tutor as an example. So because we know that the x tutor is generated without any information on the y, because we say that x tutor will be independent to the y given other x. So as a result, x1 tutor will have no direct effect to the response y. And because x1 and x1 tutor will will be indistinguishable for other features. So as a result, the indirect effect to the y for other features will remain the same. So as a result, the only difference lies for the association scores G1 and G1 tutor lies in the direct effect on x1 to the y. So if the none is true, we say the direct effect is 0. So this figure will become symmetric on the top to the bottom. So as a result, we will expect the G1 and G1 tutor will behave similar. On the other hand, if the x1 have a non-zero direct effect, which means the none is not true. So as a result, we will expect the association scores G1 will dominate the G1 tutors. So this is a gap between the true hypothesis, the two important features and unimportant feature. So as a result, we will select those features as important if the corresponding association scores GJs dominate its corresponding knockoff copies. So based on this procedure, several methods have been proposed to select the important features with a family-wise error rate control. The first procedure is the one proposed by Jensen and Su in 2016, where they developed a general procedure for K-family-wise error rate control in selecting important features. However, we have identified that the methods will be conservative when the classic family-wise error rate is the study target, because when people are using the classic FWER, it means that the K will equals 1. So as a result, they will lead to a power bound of 2 times alpha, where the alpha is the target FWER level. Another procedure is the one published by our discussions today about the randomization knockoff, which can achieve the family-wise error rate control indirectly by control the per family-wise error rate. However, this method will require multiple runs of knockoff sampling and knockoff implementations, which will be computational intensive. And more important is that both procedures may not be easily to adopt in large-scale genetic studies, because both require access to individual observations and may be infeasible due to the privacy issues and computational resource limitation. And both methods we have identified they are conservative in the power because the usage of a single knockoff. So for each time, it only generates the one knockoff for inferences, and which will be making them a little bit conservative in power. So to tackle these issues, we have developed methods to making use of the ghost knockoff methods proposed by my advisor in 2022, incorporating with the multiple simultaneous knockoff, and also we develop new family-wise error rate control filters that can provide us tighter control of family-wise error rate. So to begin with, I'd like to introduce what my advisor has proposed before about the ghost knockoff. So in ghost knockoff, unlike most of the knockoff methods require access to the individual data, our methods only require 2 inputs. The first input is the z-score of marginal association between each features and the response, and denoted by the equation 2 G1 to GP. And also what we require is the correlation matrix of the feature, where we denote by the sigma. And both components, in fact, can easily provided in the existing large-scale genetic data sets which have been published. For example, to obtain the z-scores of each features and with each genetic variance to the disease of interest, we can justly inverting the marginal association score p-values provided by most of the large-scale genetic data sets. And using the inverse by inversing the CDF of the normal distributions. And more importantly, because we are using the z-scores, which is depict the marginal association, we can allows us to perform a meta-analysis to obtain a meta-analysis z-score, which incorporating information from multiple large-scale data sets. Another component required is the sigma, which is also depicted by the LD matrix of genetic variance in the study set population. And this is also very flexible because we do not need even when the in-sampled LD matrix is not provided in the study we are interested, we can also use some LD matrix from other reference study with the similar study population of our studies. So as a result, both input are very easy to assess in the practice of genetic studies. So based on the Z's and the sigmas here, but in the paper of 2022, it is a proof that when the Gaussian model is imposed on the features x, where it denoted by x follows the normal distribution of 0 and sigma, the knockoff copy of these scores representative can be generated follow the equation 3, where the knockoff copy is denoted by z tilde 1 to m. So here we have that the calculation only required several steps. First, we can compute the matrix P, which is a block matrix with n block, each block containing a P times P matrix, and then times to the original observed z scores. And then we also plus a random error E tilde, which is P times m dimensional random vectors. So where the E tilde is follow a normal distribution with mean 0 and covariance matrix B. So here we can see that there are two undefined matrix D and the C. So the D matrix is a diagonal matrix that we have defined similarly in the knockoff procedure where we have the covariance matrix between x and x tilde will equal to sigma minus D here. And the C matrix is computed by both the sigma matrix and the D matrix. But however, here after we have observed this, we have identified this in fact maybe come to some computational issues, because when we say we want to generate the Z tilde, we need to sample a P times m dimension random vectors E tildes. And for example, if we take a simple consideration, when P equals 1000 and then we take a m equals 19, the dimension of V is in fact 19,000 times 90,000, and which is to be computational intensive. And in most of practice, we in fact do not use the small number of P's in fact. So as a result, we have considered how we can make the generation of the knockoff copy of these scores in a more scalable way. So we propose an efficiency algorithm to generate the U tilde using the structure of V. So we have observed that in fact we have a large scale V. In fact, we have a very easy. We can be decomposed into two matrices V1 and V2, and each one can be denoted by the canonical products between the M times M matrix and the P times P matrix. For example, for the V1, the first one is the M times M matrix of the ones, and the second matrix is the P times P matrix C minus M minus M minus 1 divided by M times D. And the second matrix V2 can also express in terms of canonical products of M times M matrix, and one matrix of the one diagonal matrix. This is a p-dimensional diagonal matrix. So based on this observation, we have developed new efficiency approaches to generate the E tildes. Firstly, we will generate a E1 tildes, large E1 tildes, which follow a normal distribution with mean 0 and covariance matrix V1. So here, in fact, the E tilde is generated in a very simple way. That we set it as the m copies of the smaller E1 tutor. Each E1 tutor will follow a normal distribution of this covariance matrix. So as a result, we will have the E1 tutor, large E1 tutor follow the normal distribution with covariance matrix V1. And for the second component, we can also generate the E2 tutors, where the E2 tutors contain the m copies of the normal distribution with the covariance matrix of the diagonal matrix D. And then we can compute the E2 following this way, such that we can make the large E2 tutor follow the normal distribution with a mean 0 and covariance matrix V2. So, and both have been proven as rigorously. So as a result, the generation of the E tutor will become very simple. We just directly summing up E1 tutor and E2 tutor into a large in the E tutor, and then we can obtain the E tutor follow a normal distribution with covariance matrix V. So we have compared the computational efficiency of the all approaches which are directly generated E1 E tutors using the classic Cholesky decomposition way and the procedural by ours methods under different dimensionality and the sample and the same knockoff copy m equals 19. So we can see that when the p goes to 500, the O method it will take about 1.5 minutes to generate the knockoff copies of Z-scores, while the new method have improved the computational efficiency to about several thousand times. So based on after we have used this new efficiency algorithm, we managed to generate, for example, m copies of a knockoff copy of Z-scores for each feature. So for example, we can summarize them in the table. For each feature, we have observed Z-scores and m multiple simultaneous knockoff copies of the Z-scores. So here we will summarize the table with the equation 6 using the important statistics kappa J's and tau J's. So here with kappa J, in fact, will indicate whether the GJ dominate its knockoff copy. So if kappa J equals 0, it means the GJ will dominate its knockoff copy. And tau J will measure how much the GJ overwhelms its knockoff copy when the kappa J is 0. So the principle is that if we reflect back to the philosophy of knockoff, we would like to select those important features whose Z-scores would overwhelm its knockoff copy by greatly. So our target here will our selection of important features will be follow this workflow. We firstly will sort the features from according to the decreasing order of tau J's. And then we will select those features whose kappa J is 0 and also with a large tau J. So as a result, we can select those features whose GJ would dominate its knockoff copy greatly. However, where should we stop to maintain the FWER control? So the terminating condition is obtained via the key property we have proven for the statistical important statistics, where we follow the classical multiple knockoff property that we have proven that the kappa J in fact are independent uniform random variable on 0 to m, conditional on all the kappa J's for not important features and the tau J's of all features. So as a result, if we have sorting the features according to the tau J from in the decreasing order, and then we keep selecting those important selecting features whose tau J is large and the kappa J is 0. So if we stop at the width on non-zero kappa J, for example, if we stop for the first kappa J, we will have that the number of false discovery before we stopping follows a negative binomial distribution with a parameter v and success probability 1 over 1 plus m. So based on this observation, we can use this to obtain the stopping rule with respect to the family-wise error rate control. For example, when the alpha equals 0.05, we can suggest to use the m equals 19. That means that we use a 19 simultaneous knockoff copies of Z-scores with and stopping selecting the important features once we have meet the first features with the kappa J equal non-zeros. So as a result, so this is the procedure we applied in both simulation and real data analysis. and we have proven that they can provide a valid family-wise error rate control. So in the next, I would like to show you some simulation to illustrate our methods manage to control the family-wise error rate and how its power performs. So here we generate synthetic data not only to evaluate our methods in both family-wise error rate control and power, and also to compare with the existing methods which also control the family-wise error rate, including what we have mentioned, the procedure of Jensen and Su in 2016, and also the randomization knockoff. So here we set the STEM target FWER level alpha equals 0.5 and use the number of knockoff copy m equals 19 for our methods as we have suggested in our filters. So in the first procedure, in the first simulation, we conduct some experiments of the 2000 randomly generated data sets with Gaussian features, where the features follows a very normal distribution with the compound symmetry covariance matrix, and we simulate the response from the linear models. So and then we have checked the empirical family-wise error rate and the power of our method compared to the existing one when we are varying the signal strength in the non-zero component of the beta. So as we can see that as the amplitude growth, the family-wise error rate of our methods does not violate the declared FWER levels. And also we have provide substantial power advantage over both existing methods. For example, we can see that the procedure by Jensen and Su we have mentioned before that it can only have a power bound of 2 alpha, so which means that here is 0.1. So we can also check that the power bound of the procedure of Jensen and Su is extremely lower, but our method can obtain a power up to 0.6. And however, this is also of course people will question that, okay, in fact this is simulated under the Gaussian model, which is the model assumption of the features we have presumed in deducing our knockoff copy of knockoff generations. So as a result, we also conduct a simulation with the features, non-Gaussian features, where each feature is generated as a linear combination of RRD uniform random variables. So as a result, we have the XJs are not Gaussian features, but we have a correlation matrix as a sigma here. So by under the non-Gaussian feature, we calculate the family-wise error rate and the power of our methods with respect to the different amplitude levels. With respect to amplitude levels. So we can see that even under the non-Gaussian features, we can have both a family-wise error rate control and still have advantage powers. The reason is that even when the feature is non-Gaussian, in fact, the z-scores in fact are also follows the approximately normals. So these scores still closely to a normal distribution. So once we have adopted the Gaussian generation of the knockoff copy of these scores, in fact the key property that kappa J's are still approximately uniform distributed for the unimportant features. So as a result, it should still guarantee the family-wise error rate control of our method approximately. So finally, I'd like to introduce how we apply our methods in the real data, which we also encounter some real difficulty and have identified some limitation of our methods, and which is for the next step research. So here in our real data analysis, we want to investigate the empirical performance in detecting the genetic variants associated with the Alzheimer's disease. So we apply our method on the aggregate summary statistic of genetic variants from non-overlapping large-scale or genome-wide association studies on individuals with European ancestry. So the details of this nice study is summarized as here with about 40 about large number of samples from both AD cases and control cases. So Because in most of practice, family-wise error rate control is conducted in the confirmative studies. So here, to mimic this situation, we can extract the Z-scores of the 98,000 variants in the PQTL that has to report to have a significantly association with the level of at least one plasma protein, so such that we have a set this about 8,000 variants of the candidate genetic variants. And corresponding to this 8,000 variants, because we are doing meta-analysis, which have not reported in sample covariance matrix. So as a result, we will estimate the covariance matrix of this 8,000 variants using the genome-wide times from the UK Biobank data, which is also the study of the European ancestry populations. And in the next, can we directly apply our methods on the Gauss knockoff on Z-scores to select those important genetic variants? Technically, it is feasible. However, we have when we do the inferences, we have identified that directly doing so is likely to miss most of our AD associated variants. The reason is that what we are using to make the inference is the marginal association between each features and the response. So, and we will firstly sorting the features in the decreasing order of tau j, and we stop when we make the first kappa j non-zero kappa j's in the selecting important features. So in here we have identified one feature that okay. In the genetic data, in fact, there exists some strong correlation among the genetic variants in some small regions. For example, this is the LD matrix of the genetic variants within the chromosome 6. So here we can find a large group with strong correlations. So in this case, if there exists a strong signal exists in one of the genetic variants in this region, for this gene is the variant is tau j will be large and the kappa j will be 0. Of course, we will select that. However, it is highly possible that we have nearby genetic variants with both large tau j's and small and non-zero kappa j, because it's not important, but its tau j is large due to the strong correlation with the strong signal. So as a result, our method will be stopped too early, because we will only stop in the strongly association regions of the Alzheimer's disease. So as a result, to address these issues, we will apply the hierarchical clustering on all the genetic variants to leading to 6,000 variant groups, such that the pairwise correlation between different groups are within the region with interval minus 0.75 to 0.75. So as a result, we shift our target from selecting the important variants to important variant groups, and then by doing so, as a result, we will aggregate the effect of all variants in each group using the test statistic of chi-square test. So under the definition that the group with at least one important variants are important, we will apply our proposed methods to identify those important variant groups with the number of knockoff copy M19 and the target FWER level 0.05. So here we still generate the knockoff copy of Z-scores. However, our inference will summarize the group the variance effect of each group using the chi-square test statistic we have mentioned in the last slide. So by doing so, we managed to identify about 42 genetic variant groups, which have been visualized in the follow, except for 3 groups in the APOE, APOC region with the strongest association to the AD, because does not show up because of the strong effect. And even we have omit those most significant, most strongly associated gene groups. We have also identified a lot of groups within 1 megabase distance to the gene, with several genes have reported in the existing rows. In contrast, when we apply the randomized procedure, we also have only identified 5 groups rejected by the procedure. The reason maybe comes from the bounded power of the procedure of Jensen and Su underlying the randomized procedures. So in conclusion, we have in this work we have developed methods to perform the family-wise error rate control inferences of the conditional independence when only a summary statistic are available, with both a rigorous FWER control and efficiency computational algorithms. However, we have also identified one potential development of our methods, which has been identified in the real data analysis. That means that the mismatch between the z-scores and the conditional independent hypothesis. So which will come to some question that we will need the genetic the features not that strong correlate to avoid the power loss because due to the early terminations. So in our so we are also working on the work that we have to circumvent these obstacles. So so this is the end of today. So this is some reference and the end of today's presentations. And thanks for your interest.
Thank you, Jiaqi. Very interesting talk. So next, let's welcome Jimei to give a discussion of this work. So Jimei, please take it away.
Sorry, I was trying to unmute myself. Right, thanks a lot for the invitation. So, well, first of all, I would like to say congratulations on this great work. So this is a really well-written paper. So I don't really have any like questions or comments per se, but because this paper apparently has considered a lot of like most of the aspects that I could have thought about. So I just want to give sort of an overview of multiple testing problems and the role of knockoffs in general, and then ask a few questions, although most of them have already been discussed in this paper. All right. So to start with, just like a background, a simple summary of the paper. So this is primarily about the multiple testing problem, and then meaning that we're testing a lot of hypotheses simultaneously. And in particular, this paper is concerned with the conditional independence testing, which is slightly different from the typical marginal testing that people do. And this, like rejecting this null hypothesis, gives us more information on what type of correlation that we're looking at. So, but rejecting one null hypothesis in this case means that we are discovering some feature that provides information that is not already given by the other features. So this is a specialty of this paper. So generally in scientific research, I typically would think of different studies and depending on what type of analysis they are. So there are studies that are more of the exploratory nature and others that are more of the confirmatory nature. And for these type of studies, people actually want different types of type 1 error guarantee. So for the former, people are more tolerant to the occurrence of type 1 error. So like a relevant type 1 error measure would be the so-called FDR, the false discovery rate, which is a measure of the fraction of false positives. And on the other hand, for confirmatory data analysis, people are more stringent about making a type 1 error because now you're sort of telling people what is the right thing to do, what is the right conclusion. So in this case, people care about the absolute number of false positives. So given this motivation, the FWER, family-wise error rate, or per family-wise error rate might be more appropriate in this case. And in this paper, the second type of error control is primarily discussed. They are proposing a method for a more stringent type of type 1 error control guarantee. However, there are many challenges, as you can imagine. So first of all, to start with, it's in general hard to even obtain valid p-values in high dimensions. So people are, I guess, more or less familiar with constructing a p-value for each of these hypotheses, put these p-values into like a multiple testing procedure, and get a rejection set. But it turns out that it has been discovered by many papers that if you are in a high dimensional regime, even like moderately high dimensional regime, it is very hard to obtain p-values. Traditional ways of obtaining p-values via asymptotics can be wildly wrong in practice. So this is the first challenge. And when you have an invalid p-value and it's anti-conservative, that means there is an inflation of type 1 error. That's something we don't want, especially in a family-wise error rate confirmatory data analysis regime. And second, there are correlation between features, which makes things harder, even if you get valid p-values. The reason is that you want to identify the true signal, and if a null feature is highly correlated with the true signal, and then if you just look at the marginal guarantee, like marginal correlation of that null feature and the response, you can also have some seemingly strong correlation, but that does not mean this is the feature that's actually causing the response to change. So that's the second layer of challenge. And also there are power issues. Sometimes you have like a valid a procedure that controls FEM-wise error rate or put FEM-wise error rate like in a very stringent way, but it often cases that you have very low power. Just imagine that you can pass your p-values to the Bonferroni correction, and then the resulting power can be pretty low in some of the cases. So these are the questions that this paper is trying to address. So these are very important questions for practitioners. So the paper actually is situated in a very special setting, and that's inherited from the Model X knockoff approach. So I want to like sort of talk about this Model X knockoff approach a little bit. So the overall setup of Model X knockoffs is that we're considering like a random design where both X and Y are from a joint distribution P of XY. So this is different from a fixed design where we assume X is given, there's no randomness in X. And in particular, this Model X approach is assuming that the distribution of the covariates are known or can be well estimated. So in a GWAS example, it means that we need to have like a understanding of how these genetic variants, these SNPs are what's their distribution like. For example, if we're assuming they're normally distributed, what their mean is like, what their covariance matrix is like. So in some of the applications, this is like reasonable assumption, because if we have just like an enormous amount of unsupervised data, we could use those data to estimate this distribution. So what knockoff does is that it's essentially creating some synthetic control that behaves similar to the feature matrix, but it's designed in a very delicate way such that it also preserves the correlation structure of the original feature X. So for example, if you have like a knockoff column and you swap it with the original column, it does not make a difference if you just look at X, the distribution of X. However, because they're just synthetic controls, so they don't have anything to do with the response. So you sort of want to contrast the relationship between X and Y and the relationship between knockoff copy and Y to find out the real signals. So that's how knockoff, like the high level idea of knockoffs, creating synthetic controls. So it has very nice theoretical guarantees. We can like prove that it controls type 1 error in a finite sample case, as long as we can estimate this P of X wall. So there are different variants of knockoffs, and so there so in two different papers. So first of all, the Jensen and Su paper, this is designed for controlling the K FEM-wise error rate. It's just a generalization of the FEM-wise error rate. And there's another version that controls the FDR. But regardless, like nevertheless, these two all control their type 1 error if the assumptions are satisfied. And in particular, this paper is based on the first variant of knockoffs, the Jensen and Su filter. So roughly speaking, so first of all, this procedure controls the FEM-wise error rate in a finite sample case. It can be proved. It's rigorous. And then the way it does it is that it shows the number of false discoveries made by this knockoff procedure can be upper bounded by a negative binomial process. And then the number, you can explicitly calculate an upper bound of the number of false discoveries. However, there are many issues remaining for this procedure. So I'm just naming a few. So first of all, in order to construct this knockoff matrix, you actually need the full X matrix, the original design matrix. So again, in the GWAS example, you need to know the full genetic variant, like genetic information for all of the individuals in your study. So that's not practical in most of the applications. And second, it's unstable because this is a random procedure. When you're generating knockoff, you have to insert some randomness to make sure that the exchangeability between the original knockoff and the original design matrix and the knockoff copy. So when you run knockoff twice, you might end up with very different results. And also it might have power issue, especially when your type 1 error budget is low, say alpha is 0.05. Typically, if you run the Jensen and Su filter as is, it could have like bounded power, which is very low. And practically, it is not usable for cases where you want a low type 1 error. And finally, the computational cost is pretty high, both because of you need to construct the knockoffs and also you need to contrast the importance of the original feature and the knockoff feature. And by doing so, you need to, for example, fit some models on this gigantic augmented data set, and that also increase the computational cost. So these are the problems in the original procedure, although it controls the different error rate, but there are things that are not desirable for practice. And this paper makes a good effort to solve most of these questions. So this is ghost knockoff. So basically the idea is that we're contrasting the marginal correlation between xj and y and the marginal correlation between x2 to j and y. So the statistic itself characterizes the margin correlation, but it's just an instrument. The test it is aiming at is still the conditional independence. So previously, what knockoff does is that it first generates x tilde based on the original x, and then it computes z tilde. But now, what the ghost knockoff does is that it avoids that step, avoids looking at x, creating x tilde, and then create z tilde. It just directly create a knockoff for the statistic z, which is the summary statistic, something you can't access based on the published data set. So that avoids the whole privacy issue or the access to data issue. You just don't need the full access to the data in order to conduct your data analysis. And second, it provides a method for generate multiple knockoff copies simultaneously. So what's the benefit of that is it sort of solves the power issue in the low alpha regime. So part of the reason why the original knockoff filter is not able to handle low alpha regime is because you can imagine that it provides a p-value, but that p-value is super, super coarse. And then you cannot reject the null hypothesis at a very low alpha. But if you have multiple knockoff copies, you sort of get a finer p-value such that you can reject null hypothesis at lower alpha. And finally, there's like a computational shortcut to make this whole process much faster. I'm putting like a star here. The reason is that this is not really a like apple to apple comparison because the feature importance statistic is sort of different in the ghost knockoff than the original knockoffs, because previously to compute the ZJ and ZJ tilde, they were fitting lasso, for example, but now it's just using marginal correlation. So that's not a real apple to apple comparison. But as a whole pipeline, this is definitely computationally very light, and you have the ability to do it multiple times. All right. So the last points that I want to make is I actually have some questions. So most of the questions have already been more or less discussed in the paper, but I would like to hear everybody's opinion on that, especially the author. So first of all, the current result highly relies on the Gaussianality and the form of statistic. You need X to be normally distributed, and you need the statistic to be in the form, like at least linear form, so that you can pass the property of knockoff itself to the feature importance statistic. So a natural question would be, what about X has other distributions, or what about what we want to work with other test statistics? So while I was preparing this discussion, I noticed that actually the group of our authors have a recent paper that sort of generalized this to another statistic that's based on Lasso. But my other question is that it seems like if you go back to the lasso type of statistic, then the computational cost would be going up again. So I was wondering, what's the trade-off here? What's the general consideration? In like especially in GWAS, what's the like primal goal, like concern in these applications? So that's my first set of questions. And second, I just want to comment on like when we talk about multiple knockoffs, there are the two actually orthogonal way of thinking multiple knockoffs. So one of them is that we have one ZJ. We have a way of generating this knockoff, but we can do it independently conditioning on this ZJ. So this is what I was working on, so-called de-randomizing knockoffs. When we run it multiple times, how can I de-randomize this procedure? And on the other hand, in this paper, and as well as an earlier paper by Jaime and James, the multiple knockoffs is in a joint way, in a sense that we want these ZJs to be exchangeable themselves. So these are, I would like to think of these as two orthogonal ways to come up with multiple knockoffs. So they're not, they don't, I feel like they don't have to compete with each other. So it's actually possible to do both. So that's the other thing I was just want to comment on. Finally, it's a more generic question about meta-analysis with summary statistic. It's just something I think about when I'm doing data analysis myself. So first of all, what if you have overlapping cohorts in different studies? How do we for example, combine the summary statistics and generate valid knockoffs? And second, how in general do we deal with missing features hypothesis when we're looking at multiple studies? Is there like a principled way of doing that? And finally, if there are heterogeneous effect in different populations in different studies, is it possible to have special treatment to say maximize the power or something like that? All right, so I'm taking up too much time, so that ends my discussion. So yeah, I'll hand the stage back to the organizers and Jiaqi.
Thank you, Zhimei. Very nice summary of the knockoff as well as the insightful questions. So Jiaqi, would you want to respond to the questions that Zhimei mentioned?
Yeah. And also I noticed some of the Zhimei's question overlap with the ones proposed in the chat room. So I'd like to go through one by one. So for the first one is about the Gaussianity assumption on the features, and also the test statistic we are using is a marginal association. So so for the first one, for the Gaussian distributed one, I have also mentioned in the talk that of course the derivation of the Gaussian knockoff depends on this assumption. However, we have identified that in practice, doing so does not provide empirically violate the family-wise average control even when the feature is non-Gaussian. The reason is that what we're generating is although we derive it from in terms of X, but how we generate the knockoff copy Z-score is based on the original Z-scores. So the most important thing is about whether the original Z-score is a Gaussian distribute or approximately Gaussian distribute. And this, in fact, it can be easily satisfied in the large scale genetic studies where we have a large number of observations in underlying each large scale genetic studies. So as a result, we can find out that the Z-scores in fact are approximately Gaussian distributed. So as a result, the knockoff copies of these scores will approximately satisfy the satisfying property of the original knockoff methods. And when we consider whether it is possible to consider any other test statistic, the answer is in fact yes. Because what we have proposed here does not worry about what is the distribution of the what is the type of response we are interested. For example, as one of the questions in the chat room mentioned that what if the Y is corresponding to the survival time to event data or survival data. So in this case, we can interpret the marginal association, the marginal association Z-scores in another way, that we can interpret it as the test statistic of test in simple univariate linear regression model. So as a result, it is possible for us to extend this to a more general form that for example, as for the z-scores of any simple regression model, for no matter whether it's regress on just regress on the response or on the survival regressions methods. So as a result, we can also apply for other test statistics. And if we say whether it is possible to apply not in the Lasso type, in fact, one of the I have found that Jimmy has mentioned our recent papers which have been put in the archive that we can use only the z-scores and the covariance matrix, and of course the D matrix computed by the correlation matrix to perform a Lasso regressions. Of course, this method is will not satisfy the similar way of the original knockout methods. They will not be exactly equivalent. However, because in this method we have also developed some computational tools in R, which have been published on GitHub, such that making use of the correlation matrix, because we have mentioned that there's a structure, a satisfying structure of the covariance matrix. We have a sigma and sigma minus diagonal matrix D. So as a result, in this procedure, we managed to adopt the structural property of the correlation matrix to enhance the enhance the computational efficiency in fitting a Lasso model, even when the dimension is large. For example, here we have a P times M, and we have can perform the PM dimension. PM plus 1 dimension Lasso model fitting more efficiently. And for the second question by Jimmy is about the multiple knockoff, the two way of multiple knockoff. The one way is the de-randomization way that it generates the multiple knockoff which conditional independent on the observed z-scores. Another way is that what we have adopted here is the multiple simultaneous knockoff that generate a multiple simultaneous knockoff that are exchangeable for each pairs for the whole m plus 1 z-scores, including the one original and the m generate a knockoff z-scores. And in fact, both methods, in fact, are functional, that they can be incorporated together. For example, we can perform the de-randomization strategies with multiple simultaneous knockoff in each implementations, and this can also may also be improved. We can incorporate the benefit of both procedures, and I think this is also possible to. We have make an initial try in our supplementary materials, but we have not get into too deep to these topics, and this may be a possible implementation if possible for the future if we have identified some possible application areas. The final question is in fact about more advanced topic, including, for example, what if we have a missing features? And in fact, we have identified this because in practice, in fact, for example, for the genetic data set, we have identified a lot of features. Not all genetic variants of all individuals will be matched with sequence simultaneously. Some people will have some genetic variants missing in the data. So in fact, under these cases, we have performed some of the investigation before and have identified that in fact this is a missing data problem. Feature problem is in fact a it is very hard to tackle. And what we can interpret is that we need to treat the missing together, making this feature as a masked feature, including those observed features and those missings. And the final question is that, okay, whether it is possible to deal with the heterogeneous problems. In fact, of course, currently this procedure cannot deal with the heterogeneous effect because it also requires the access to a lot of individual level data. In fact, but what we have another work has recently working on using applying the knockoff in the scenario that we have a heterogeneity among the effects of each of features for these individuals. And of course, this is not for the summary statistics because it also requires more information on each individuals. But so this is I think this is the most of my now I had currently have for your questions.
All right, thank you, Jiaqi. So, in the interest of time, we may not be able to go over all the questions in the chat, but please feel free to reach out directly to Jiaqi or the co-authors of the paper to get those questions addressed. So, with that, I would like to thank the speakers again and also the discussant for the excellent talk. I'll hand it back to the International Business Office.
And thanks, Jen, and thanks to our speakers and our participants today. On behalf of IBS, thanks for joining us. We will be sending out information shortly regarding the next journal club, so stay tuned for that. Reminder, a recording of this session will be available on the IBS website early next week. And we hope to see you in Atlanta at IBC 2024. So scan that QR code and you'll be taken to the IBC website to learn more about the scientific programs and all the exciting opportunities available. So with that, we hope you enjoy your weekend and hope to see you at the next Journal Club. Thank you.
Thank you, everyone. Have a good one. Thank you.
Thank you.
Thank you, Jimei. Thank you, Jiaqi. All right. Talk to you later. Bye.
Bye.